Hi, in this presentation we are going to talk about the paper What Does It Mean to Understand a Neural Network by Tim Lillicrap and Konrad Kording. By the end of this talk, I hope that you will be able to have more clarity on what the word understand actually means, because it's English language, right? People use it differently in different contexts. So I hope we have a better definition of it. And I also hope that you'll be able to summarize the main point of this paper and its supporting arguments, and hopefully also form your own view on if this paper makes sense or not. So here's the flow of the presentation. We are going to first define what understand means so that all of us are on the same page. And then we look at the overview of the paper, and I've organized it in a very specific way. We'll have three claims that the paper makes and the logical conclusion it draws from these claims. And then we go into each of those claims in detail, and then the conclusion, and then we discuss some caveats. So, what does it mean to understand a neural network? And I think this is how understand is defined in the context of this paper. But if you're this is not a philosophical or linguistic definition, and people, when they use it in the real world, they use it in very different ways. But so when I was reading the paper for the first time and I was trying to understand the arguments that they're making, I found it hard because they did not actually define understand. So, based on my based on how I interpreted the paper, I came up with my own definition of understanding and tweeted it to Konrad, and he liked my tweet. I don't know if it's an endorsement, but I think it's kind of evidence that we're not completely far off using this word in with this definition in the context of the paper, of course. And so this is how we are going to define the word for this paper, and it's defined again very roughly. So uh, here are some rules or properties that an entity should follow if we were to say we understand it. Number one, it can be compressed into few rules. Number two, we can improve and build variations of it. And number three, we can tell human-centric stories of what's happening. And in short, I would call them compressibility, improvability, and anthropomorphizability. And again, all of these are words in English. People use it differently. People might not agree on what is compressible and what's not. These are all very subjective words, and I also tweeted to Konrad asking him if he had a more objective definition in his mind when he was talking about it in the context of this paper, and he responded saying, "None of these objective metrics." None of the objective metrics for understanding will be entirely satisfactory. So I think even he doesn't have a mathematical definition for objectivity. We're still using human words, but we're just decomposing it into specific principles so that we have more consensus. So let's take a few examples to understand what understanding means. I shouldn't have used it that way, but uh, let's take a few examples to clear up this definition. So let's think about an unbeatable policy of tic-tac-toe and think about it. So apparently, the unbeatable policy in tic-tac-toe can be decomposed into just three rules. And what we're basically trying to do here is to explain various policies using anthropomorphic rules. So you just need three anthropomorphic rules to explain perfect performance on tic-tac-toe, and you can see that this satisfies all the definitions of understanding that we had. Uh, we uh, I'm going to call these three in short as compressibility, improvability, and anthropomorphizability. And we can see that it is compressible because you have very few rules. It is anthropomorphizable because all these rules are anthrop- anthropomorphic in the sense that take a corner. It's a very human centric understanding of the tic-tac-toe world, and it's also easy to improve or build variations of it by just changing a rule here. So just replace it with something else and we have a variation. So it's quite easy to build variations. And let's so now that all of us see that tic-tac-toe satisfies these definitions, let's spend some time thinking about Go. How can an unbeatable policy in Go be decomposed into rules? And the authors hypothesize that there wouldn't be a small set of rules, and you'll need lots of anthropomorphic rules to explain this unbeatable policy. And for that reason, they say it is not compressible, and hence it violates our definition of understanding, and hence this is not understandable. And then they say it's helpful to think about where the brain lies on the spectrum. uh, brain can still be thought of as something that is mapping some inputs to some outputs, and we how many anthropomorphic rules would we need to explain this relationship? So now that we have the same definition for what the word understand means, let's get into the paper. So this is the paper in just one slide. The paper is an opinion piece on how neuroscientists need to go about understanding the brain. Uh, so they make these claims and draw the conclusion from them. So claim number one is, this is not exactly the format they follow. I've reorganized it this way because I think it makes the point much more clearly. Claim number one is that it's easy to understand the development principles in a deep neural network. And again, I haven't defined what these words are. We'll go into specifics of each of the claims further, but I'm just stating the claims for now. It's hard to understand. Claim number two is that it's hard to understand the resulting properties after training a deep neural network. And that both of these claims also seem to apply to the brain, and hence we need to focus on development principles of the brain instead of the resulting properties. And as we keep talking about each of these claims and going in more detail, it would be nice if you could try to form your own opinion. And another disclaimer here is that I might not have done complete justice to the paper, in the sense that their words are much more conservative than what I use in this presentation. The content remains the same, but the tone is much more conservative in their case. And I didn't want to include all the subtleties because I think it gets harder to parse if I'm including all of them in the presentation. I just wanted to keep it simple and straightforward. But yeah, just keep this in mind that the authors are much more careful with their use of language. So claim number one, they say that we understand the development principles of a deep neural network. When I say development principles, what I mean is the data set, architecture, learning rules, objective functions, and stuff like that. So all of these high level principles specifying how you train your deep neural network. And these development principles satisfy all properties of understanding. For example, they are compressible because you need less than 100 lines of high level code specifying these principles. It's improvable because it's easy to add some kind of regularization term to the objective function, and you can get a better architecture with this normalization term. So it's very easy to come up with ideas to improve what's already there. And we can also talk about this in with human-centric stories of what's happening. We can say this is the architecture, and then this is the data set. You send a batch of it, and then these learning rules tweak your connections in specific ways so that you're optimizing the objective function. So you can tell a very human story of what is happening with the development principles. Hence, they claim that we understand a deep neural network, the development principles of a deep neural network. However, they say it's hard to understand the properties of a trained deep neural network. So, when I say properties of a neural network, I mean the computational graph and the corresponding weights that you get after training the network. And they violate the properties of understanding that we had before. Uh, let's run through each of the properties. So, property number one was compressibility. If you're training AlexNet on ImageNet, you have millions of parameters, and that's certainly a very high number, and you can't call it compressible. Work has been done to distill the parameters down, and you get down to 100K, but it's still a very big number. And they say it's not improvable because given the weights of the network, it's very hard to improve unless you go back to these principles. So if you train your AlexNet on ImageNet and you want to include a new class, it's very hard to uh, figure out how you want to change or tweak your weights to include this new class unless you think about it from the development principles. Without using any of them, they say that it's too hard to understand or improve the network. And it's also not anthropomorphizable because in the case of AlexNet, where we brought it down to 100K parameters, none of them seem to be human understandable for the most part. I mean, you could say we do understand it to some extent, that we understand that the initial layers are looking for low level features and the later layers are looking for high level features. But they do mention that in the caveats that I'm going to talk about a bit more. And another problem is if someone asks, why did you classify that image as a dog? We don't have a human centric story of what's happening for any of these adversarial examples. So they do acknowledge that a lot of work has been gone into figuring this out, the problem of interpretability in machine learning. And some of the attempts include asking which stimuli fool the system, visualizing these internals, removing nodes, and they say that none of these actually offer a good understanding because these properties are still mostly violated. So we have argued that a trained deep network is not compressible and hence not understandable. So let's try to extend this logic to an artificial general intelligence system. So what do I mean when I say AGI? I mean that we're talking about a system that is at least as good as humans in a broad range of tasks. Uh, and for example, let's consider tic-tac-toe and Go. Let's consider a system that is good at tic-tac-toe and also at Go. If we look at just these narrow systems that just work on tic-tac-toe and just work on Go, we've previously seen that it's very hard to compress Go. So they say that if we have an AGI system that can solve both of them, in principle, it won't be compressible either. It would be at least as complicated as Go. And Sam raised an interesting point when I shared the slides with him, saying, how do we even know how this AGI system looks like? Maybe it doesn't have weights at all, which is a very fair point, and I agree that we can't be completely certain of this claim, and I think the tone of the authors also is in line with that conservatism. And so the point that we're making again here is that it is more promising to focus on principles than looking at the trained weights. And they claim that the above claims also apply to the brain. They say while the brain is not an artificial neural network, it can be thought of in similar terms, and they write this function. So in the case of artificial neural networks, we can think of this function in a specific way. So the function is uh, a the function takes in the data set and principles. When we say principles, we're talking about the architecture, learning rules, loss functions, etc. of the network, of the artificial network. And then uh, with these principles and the data set, what you can get is the computational graph with the weights as output. So this is your training function. And they say the brain can also be thought in a very similar sense, in that the final training weights in your deep network resemble the present brain state, which includes the architecture of how they are connected, uh, and also the synaptic strengths. And the data set can be seen as the input you get from all senses, and principles uh, could be the architecture, learning rules, loss functions, and more high level ideas like that in the brain. And they they put in this figure to show that how potential principles in neuroscience could look like. In machine learning, we have an architecture of connections between various nodes, and they say in an we can have same thing neuroanatomically, where we have multiple nodes connected, and we can again analyze this at various levels. We can either go to the single neuron level or the population of neurons level. And the machine learning algorithms generally have the gradient descent kind of learning rule, whereas the brain probably satisfies something more like the STDP rule. And Blake Richards and his colleagues take this further and argue that neuroscientists would benefit with focus on cost function, architecture, and learning rules of the system, especially in neuroscience, instead of trying to understand the computations of individual neurons. And they also give a framework in which scientists running wet labs can have can change how they do experiments in light of thinking in this framework. And so this is what we covered in the paper. In this presentation, we discussed various claims. Claims were that it's easy to understand high level principles, it's not easy to understand the resulting properties after training the network, and both of them apply to the brain too. So we need to focus on understanding high level principles of the brain rather than the resulting properties. And again, I'm you the tone is much more stronger here than what was in the paper. And there are also a few caveats. They say that we may eventually be able to understand a trained network, or maybe it's impossible to meaningfully understand such a network, in which case we want to find ways to prove that. And maybe humans can't understand it, but potential superhumans can. And in any of these cases, they say that neuroscientists need to think about it carefully, and lots of methods that are presently used, especially trying to understand things at the single neuronal level, may just not be able to deliver results. And that's the end of the presentation. Thank you for your time.